Fortunately, someone was able to let us in because I am the chair, but I'm not the organizer. And being located in Delft, I'm also not able to. Well, I also need to get in. But we succeeded, and fortunately, we have some participants.
Okay.
Given the time, I suggest that we immediately start with the meeting, and I would welcome you all to the Circular Industry Talks of the LDE Center for Sustainability. I am very glad to introduce John Allen Pascoe, who will today discuss circular aviation with us. And John Allen is an assistant professor at the Aerospace Engineering Faculty of Delft. And circularity in aviation poses challenges that differ from the products that most of us are more familiar with. John Allen will introduce us to the unique challenges of making circular structures circular, aviation structures circular. So, John Allen, please go ahead.
Yes, thank you very much. Good morning, everyone. Thanks for the introduction. As Ruud already said, my name is John Allen Pascoe. I'm from the Faculty of Aerospace Engineering, and I'm in the Aerospace Structures and Materials department. I'm also very happy to see a lot of my colleagues here today. And if everything went well, now you should be able to also see my slides. Yeah, and I wanted to discuss today what are the challenges to going to a circular economy model, or to make aerospace engineering circular, especially from the point of view of the aircraft. And based on my background, I work on fatigue, damage tolerance, and certification. What some of those terms are will become clear during the talk if you're not familiar. And with that mindset, I'm going to discuss circularity in the aviation industry. And I thought to start off with, I would start with this picture, which is a so-called aircraft boneyard. This one is in Victorville, which is in California in the US. And if we put on our circular aviation caps, what do we think about this picture? Don't know if anybody has any thoughts, make it a bit interactive. Does this make us happy or sad if we want to look at it from a circular aviation point of view?
There's not a lot going on at the moment, as you can see.
Yeah, exactly, right? So you might say, well, this doesn't look so good, right? There's a bunch of old aircraft, disused aircraft that just parked out in the desert and they look kind of abandoned. So it suggests there's a lot of room for improvement, what we do with circularity. But I also show actually this picture, and I'll come back to it later, shows that there are things that are not so bad in the aviation industry. So there's some aspects of circularity where a lot of improvement is needed, where there are a lot of challenges, but also some aspects where the aviation industry actually does a really good job. And I'm going to cover both of those today. So the next thing I want to introduce you to is this chart. If you are familiar with circularity, you've probably seen some variations of it. This is sometimes also called the R ladder, although in this formulation, not all the words start with an R, right? But this is showing all the different options we have if we want to go to circularity. So ideally, we prevent that we need new products at all, because then you don't need new resources. If you can't do that, then at least reuse as much as possible of what you can have. If that's not possible, repurpose and so on. And yeah, if all else fails, okay, then you can dispose of your material. But ideally, you try to stay as high in this pyramid as you can. So the first point is prevention. So how do we prevent needing new products? So in our case, how do you prevent needing new aircraft? Well, and that's tricky, because then if you want to prevent that you need new aircraft, you have to make sure that you never reach the end of life of your aircraft, right? And there are various challenges for that. There's wear, there's corrosion, but an important challenge that makes prevention, so makes having a long lifetime of your aircraft difficult, is what you can see in this image. So this is an incident that happened about 15 years ago now, during a flight from, I believe, Phoenix to somewhere in California on a Southwest Airlines flight. And you can see that little lip of metal. There's over here. This is not the sunroof option on the aircraft, but this is, in fact, as you can see a bit more clearly when we zoom in, a fatigue failure. So this is a piece of the aircraft skin that's ripped open. You can see along these joint lines, and that of course reaches the pressure hull of the fuselage. So the fuselage is pressurized to keep all passengers comfortable. So when this happens, then all the air goes out. The passengers have to use those oxygen masks, and they have a rather exciting but not very pleasant flight. Fortunately, in this case, the aircraft did manage to land safely. No one was seriously injured, but still, this is not what we want to happen, right? What actually happened here? Well, they investigated this. They were able to trace it back. So the plane was built in 1996. But during the manufacturing, something went wrong. Some of the rivets were installed incorrectly. So as you saw, this failure is along this rivet line, right? And some of these rivets were installed at an angle, which means that this hole, if you look, it should be a circle, but you can see that's actually an oval. Because of that hole being the wrong shape, there was a bit of play in the joints, so these parts could rub past each other. The stresses were not distributed correctly, and so very soon, about a year or so after the plane was built, the material started to crack due to these increased stresses. Right? We have a phenomenon called fatigue. So if we have repeated loading on a piece of material, that can start to damage, and that damage grows over time. It's quite a slow process because it took another 12 years, 13 years before finally the crack got large enough that the remaining material could no longer carry the loads, and this entire piece of fuselage just unzipped and let out all the air. Right, so obviously this is something we want to avoid, this phenomenon of fatigue. It can happen if you incorrectly manufacture your plane, but even if you perfectly manufacture your plane, still you could have issues with fatigue. Right, so one thing is if you want to have a plane that lasts long enough, or it lasts forever, you need to design it against fatigue. So one thing you could do is you could characterize the fatigue properties of your material. We typically do that with something called an SN curve. Here's an example. So on the vertical axis, we have the stress that we apply, so the amount of load in our structure. And on the horizontal axis, we have the time until the material fails due to this fatigue cracking. Right? And we usually express that in the terms of the number of cycles of loading. So that could be the number of takeoffs and landing of a plane, right? If you have a fuselage that's pressurized once and then deflated once every flight, so it's one cycle per flight. But if you have something that's vibrating, then you might have lots of cycles even within a second. Right? So if you look at this curve, you see, okay, it starts over here. This is what we call the tensile strength of the material, right? So that's where the material fails immediately, after even one cycle. But you see there's also kind of an asymptotic behavior. So you could say, okay, that's great. We seem to have this kind of lower limit here. So if we just keep our stresses in our material below this level, well, then we would have an infinite life, right? And we could just use our plane forever. So great. Why don't we do that? Well, there's an issue. That is, if we want to have an infinite life, you see, we need to keep our stress quite low. And what does keeping stress low mean? How do we achieve that? It means we need to use more material, right? If I take a shortcut, with apologies to all the structural designers out there, but if we have more material, we can distribute the loads over more material. And that means the amount of loading, the amount of stress, so the load per unit of material is less. So the material is less highly loaded, and therefore we have an infinite life, right? So to get an infinite life, we need to use a lot of material. And to use a lot of material means a lot of weight that we have to add to our structure. Why is that a problem? Well, that is because of physics. I'm going to have some equations here for those of you who like equations. For those of you who don't like equations, feel free to zone out for a minute and I will explain the key things you need to take from the equations at the end. Right. But if we look at an aircraft in flight, there are four fundamental forces. There's thrust moving the plane forward, which is opposed by the drag on the plane. And thrust we get at the moment by burning fossil fuels. The plane is kept up by lift, which counteracts the weight of the plane. And if we're flying just straight and level, then the lift has to equal the weight, to keep everything in balance according to Newton's laws. And for the lift, we have the following equation. The lift depends on the lift coefficient, which depends on the design of our wing and the angle at which the wing is with respect to the air. It depends on the air density, which is just a function of the altitude, the speed that we are flying at, and the surface area of the wing. Right? So if we have a certain wing design, we're flying at a certain speed, the pilot will adjust the angle of the plane to get the right lift coefficient to keep everything in balance. And that means, what is the right lift coefficient? Well, you can solve this equation. And the key thing to remember from this is, if we're flying at a certain height and speed with a certain plane, which has a certain wing area, then the lift coefficient will depend on the weight. So the heavier the plane, the higher the lift coefficient. And the reason that that is a problem is because we also have the drag, right? The drag is what causes us to have to burn fuel, because if there was no drag, we would not have to burn fuel to go forward. The drag has a similar equation to the lift, but now we have this value of CD. This is the so-called drag coefficient. And if we look at the equation there, well, then we see that the drag coefficient is a function of the lift coefficient. One aspect of the drag is the so-called parasitic drag. That's always there. Another aspect is the induced drag, which is kind of a byproduct of the lift we need to generate. Right, so the drag coefficient is a function of the lift coefficient, but the lift coefficient is a function of the weight. Right, so the key point to remember from these equations is, if we have more weight, we need more lift. If we need more lift, we get more drag. And if we have more drag, we need to supply more energy to get from A to B. Right, so the heavier the plane, the more energy it will take to get the plane from A to B. Right? And if it takes more energy, that means we're generating, all else being equal, more fossil fuel emissions. We're generating more environmental impact by extracting whatever we're using as fuel. Right? So we want to avoid the weight from a cost point of view, but also from an environmental impact point of view. Right? A lighter aircraft, all else being equal, is more environmentally friendly. And we can reinforce it a bit more if we look at some life cycle analyses. So here is a study done by one of our master students some years ago on the supervision of Irene Fernandez-Villegas, for those of you who know her. And the student looked at one particular part of a plane. This is a rib. It's part of the wing. So this is the kind of structural part that helps maintain the shape of the wing. The skin goes around the outside of this rib. And the rib you could make in different ways from different materials. So what you see here on the left is different options for making it from an aluminium alloy. And if you look at the right, you see the different options for making it from a carbon fiber material. And what you can see is that the aluminium rib would be substantially heavier than the carbon fiber rib, right? So the aluminium rib is 3.6 kilograms. The carbon fiber rib is 2.1 kilograms. So it's about 30% weight savings by switching to this carbon fiber material. And then what you can see on the bar is, if you make 100 of these ribs and you install them on a plane, you fly around with the plane, how much CO2 is being emitted due to building and flying these ribs around, right, over the lifetime of the plane. And so you can see here, there's different amounts. You can see the aluminium ribs, 3.6 kilos, they are higher, the carbon fiber ribs are lower. So what you see in yellow are the emissions over the lifetime, right? So these are the emissions due to the fact that we have to burn fuel to move this rib from A to B, right? And we can't leave the rib behind because the rib is a structural part of the aircraft. If we leave the rib behind, the wing collapses. Not quite as dramatic as that, but so we need to take this rib with us. We don't have a choice. Yeah, so that's the yellow part. The green part is the amount of energy or CO2 released due to recycling. And the blue part is due to material. And the gray part is due to production. And then you might say, well, I don't see a blue and a gray part. Well, that's exactly the point. They are there, but they are tiny, right? So there's this little tiny blue sliver you might just see, depending on how big the slide is on your screen, right? But the impact of these ribs is dominated by the operational use phase, by the amount of fuel we have to burn to fly the rib around, and the amount of CO2 during production and raw material extraction is negligible compared to this use phase, right? So you can see, if we want to get a CO2 reduction, if we manage to reduce the weight, then we get a huge reduction in CO2. In this case, actually also the raw material extractions may be a bit more efficient. But the point is, if I can make my manufacturing more efficient in terms of CO2 or energy use, but at a cost of increasing the weight of my structure, it is not worth it from a life cycle point of view, right? It's always better to have a lighter structure, even if it would have a bit more manufacturing impact, in fact, because the use phase is so important in the overall emissions that you will earn that back by having a lighter structure. Right? Here's another way to look at the same statement. This is from the D-Standard project that I'm involved in, where we did a life cycle analysis, also on an aircraft component. And what you see here, this is in terms of cost, but for CO2, the relationships will be pretty similar. What you see in this graph is on the horizontal axis, the lifetime of the aircraft in years, and on the vertical axis, the cost in pounds per ton kilometer, right? So this is how many pounds does it cost to transport 1 ton by 1 kilometer with this aircraft. And what you see is that at first, if you make the life of the aircraft longer, the cost per ton kilometer goes down because you can spread out your manufacturing costs over a longer period of time, right? But at the same time, of course, your operational cost is going up because you're burning more fuel because you're flying the plane for longer. So what you see is after, about, 10 years, your manufacturing cost you fully earn back. And then, yes, if you keep flying longer, you're spreading out your manufacturing cost over longer. So also your manufacturing environmental impact, you're spreading out over longer. But also you're generating so much impact with the operational phase that additional benefit of spreading out the manufacturing cost becomes almost negligible, right? It goes down by 0.07%. So again, after about 10 years, there is no cost benefit to extending the life of the aircraft from this point of view, right? Because the operational costs become so much more important, such much a larger fraction of the total cost than the manufacturing cost. And then you might think, okay, that's now where we're burning fossil fuels, but people are very hard at work at generating alternative fuels, zero emission fuels, right? So in future, we will going to fly on electricity or sustainable aviation fuels or liquid hydrogen. They don't emit CO2. So yeah, then the story will change, right? Then the operational impact will be low because there's no CO2. So we should then really focus on the manufacturing, right? Or maybe it's okay to be a bit heavier if that gives us less manufacturing impact. Well, that would be great if it were true. But we had another master thesis study who looked into this. This is Thomas Arblaster. He looked at multiple scenarios. And what you see here, the 4 different colors are 4 different manufacturing options, 3 composite ones. That's dark orange, the purple, and the blue. The light yellow or orange one is aluminium alloy, which is heavier again. Comparing all kinds of different impact categories and planetary boundaries, right? So there's climate change, but also acidification, ecotoxicity, eutrophication, human toxicity, resource usage, and so on. On the left, you see if we fly on sustainable aviation fuels. On the right, if we fly on liquid hydrogen. And what you see, the key thing is still that this yellow bar is still higher, right? So even so, the heavier solution still has in nearly all categories a higher impact than the lighter solution. Right? So even if we fly on sustainable aviation fuels or liquid hydrogen, the life cycle impact is still dominated by the use phase, and the key driver for how much energy or how much impact we have during the use phase is the mass, right? So even if we switch away from fossil fuels, from a life cycle point of view, having a lower mass is better, even at the cost of an increased manufacturing impact, right? So flipping that around, if we can reduce the manufacturing impact, or if we can increase the recyclability, but at the cost of extra mass, that is probably not worth it for an aircraft, right? Which is very different from many other product categories where you say, well, maybe we can accept a little bit more operational impact if it makes recyclability better. But in aircraft, really, the operational impact is paramount. So what do we do in an aircraft, right? To keep that mass down, we say, well, we accept a limited lifetime. We say, well, going right all the way to infinite life, that is not good. It would be too heavy. We can reduce the weight if we allow a bit more stress. If we say, well, let's allow 100 megapascals in this example, then we will have a fixed lifetime. We divide that by 3, and then we got what's called the safe life, which essentially becomes a use-by date for our aircraft or our part, right? We say, okay, our plane, after so many flights, you scrap it. We can't keep using it because we cannot guarantee that it is safe, that it will not fail due to fatigue. We just scrap it, right? And so there's a trade-off between having a lower operational cost or lower operational impact because we now have a lighter plane, so we can fly more efficiently, but at the cost of now having a limited lifetime. Now, one issue with this approach is that if you look at this graph, it tells you nothing about what happens to the material during this lifetime. It just tells you at this point we get failure, but we don't know what happens before. And we know we have a large scatter. That's a large uncertainty, but we cannot, with this information, tell, can we keep using the plane or not? We cannot inspect the plane and say, oh, this is about to fail, or it's about to keep, or we can safely keep flying. So actually in aviation, for many cases, we've switched to a different approach, the so-called damage tolerance approach. What is the idea there? Well, fatigue, as I explained to you, is a result of cracks that slowly grow over time. Right? And so if we can predict or measure how the cracks will grow over time, then we can say, well, at a certain point in time, the cracks are large enough to be detectable. We can find them during an inspection. And sometime later, the cracks will become so large that the plane can no longer carry the required loads, right? That the plane, that the residual strength of the plane is too low, and then our structure fails, right? Or at least there's a danger of failing. So if that means that we have a certain time window between when we can find a crack and when the crack is really a safety issue. So if we divide that up into typically 3 inspection intervals, we can say, well, if we inspect the plane every so often, then we have 3 chances to find the crack. Yes, so even with one time the inspections on Friday afternoon and the inspector was rushed because he or she wanted to get home early, still there are 2 more chances to find the crack, and the crack will be larger, right? So in this way, we can ensure that we always find a crack before it's critical, right? So instead of a use by date, we go to an inspect by date. I think a bit of what they now advocate in the Netherlands, you know, if the use by date on your milk or your yogurt is passed, don't throw it away immediately, but, you know, just, you know, smell or carefully taste or have a look, maybe it's still good, right? Same we can do with the plane. So, okay, we can inspect. If we don't find any cracks, well, we can assume that the plane is still good. We can keep flying until the next inspection and potentially keep flying forever, right? Or at least until we find cracks, and then we need to take some action. So that's a so-called damage tolerance approach. Unfortunately, this also has its limitations. And that was shown by this very famous incident, the Aloha Airlines accident in 1988. So Boeing 737. And I think even those of you who are not so familiar with aircraft may realize that there's a part missing over here. Right? So this is in fact a large chunk of the fuselage that flew off during the flight. Unfortunately, one person also did not survive. There was a flight attendant who was walking through the cabin at the time who got sucked overboard. Everybody else was in their seat with their seatbelt fastened, and so they managed to survive safely. Of course, this was investigated to understand what happened and was found, okay, this was a very heavily used aircraft, had 35,000 flight hours, but over almost 90,000 flights, because it was used for flying between islands in Hawaii, so very short flights, lots of flights in a short amount of time. In a very corrosive environment, right? Warm, humid, salty. And it was found that there was a failure of a longitudinal riveted and bonded lap joint. So along this fuselage barrel, it's made of overlapping panels. And one of those joints where the panels overlapped, they found there was a collection of cracks kind of joining together all these rivet holes and then just unzipping the whole joint. As people start investigating it further, they realized there's this phenomenon called multiple site damage, MSD. And what happens is you have these small cracks, but they don't grow independent from each other, right? If you have a location with multiple holes, you might have multiple cracks starting, one at each hole. But as they grow towards each other, they start influencing each other, they start interacting, and they can even link up. And so what happens, you can go from 2 relatively short cracks to 1. Here you have a crack that goes from here to here, it's relatively short. But the next stage, now you have a crack going from here to here, all in one go. Right? So your crack very rapidly gets very much larger. And that means this damage tolerance approach doesn't work because the small crack may be too small to detect easily, but as soon as it links up, you suddenly have this jump in the crack length. And so you cannot inspect in that small time interval that the crack, before the crack links up. So that limits the damage tolerance approach. And therefore, what you now see, if you look in the regulations, This is one of the European regulations. There's one section on what they call damage tolerance and fatigue evaluation in structures. And one of the aspects you can read in there, it says that a limit of validity must be established that corresponds to the period of time for which has been demonstrated by full-scale fatigue test evidence that widespread fatigue damage will not occur in the airplane structure. Right, so full-scale fatigue test means literally building an entire plane, putting that in a huge test setup and just applying loads and seeing when it fails. And then you, based on that, establish a limit of validity. So the limit of validity means you have a certain amount of evidence from your full-scale fatigue test that you do not have to worry about about widespread fatigue damage or multiple site damage for a certain period of time. That evidence has a limit of validity. Beyond that, the evidence is no longer valid. You do not know what will happen. And what that means is that when you reach that limit of validity of your evidence, you have to stop flying. Right? It is not allowed by the regulations to continue flying after the end of the limit of validity. If you want to keep flying, you have to first extend your limit of validity, which means doing additional experiments, additional tests to prove that you can now extend that limit of validity. Maybe you also have to do some modifications to your aircraft or some repairs or reinforcements, right? But if you do not do that, if you do not put in the work to extend your limit of validity, you have to stop flying. And that may sound like a term that sometimes comes up in discussion of circularity, which is planned obsolescence, right? This is in effect what the regulations say. You have to establish a hard limit of lifetime of your aircraft. Beyond that point, you are not allowed to keep flying, period. Right? And that's not for economical reasons to make people money. It is a safety matter, right? We cannot fly beyond this point because we cannot guarantee that the plane will remain safe. So that's kind of a fundamental tension if you want to go to this concept from circularity of using things as long as possible. There are really physical safety reasons why that is hard to do for an aircraft, right? Unless you are able, of course, to keep stretching your limit of validity. So that is a thing you could do. You could say, well, I could keep investing in extending my limit of validity ahead of how I'm flying, right? But still at some point you might come into the point where you need so many modifications to your structure to avoid widespread fatigue damage that becomes very expensive to do. And the other thing you could ask is, we've seen before that the impact of the use phase is so much higher than the impact of the manufacturing phase. Is it really better to keep flying with a plane for 40 years? Or would it be better to replace a plane every 10 years if that means that you get improvements in technology which give you lower environmental impacts? I'm not saying one or the other, right? But that's something you really have to look at a systemic and life cycle point of view to understand what would be better. So that is the prevention part of the pyramid or the R ladder, right? So key points to remember. For the life cycle impact of an aircraft is driven by its mass. The higher the mass of the aircraft, the more energy it will take to fly, the higher the life cycle impact will be. So typically, if we want to fly longer, all things being equal, we need to make the plane heavier so we can keep the stresses lower and slow down this fatigue process. And safety, needing to guarantee that the plane will not fail due to fatigue, leads in effect to planned obsolescence, and that's even written in the regulations for aircraft. Then, Jos, do you have a question or? Maybe that was an accidental unmute then. Yeah, all right. So that was prevention. We've seen, okay, we cannot use a plane forever.
You're muted now, John.
Yeah, I should be unmuted again. So the next step, if we move down the ladder, if we can't prevent that we need to dispose of the plane, well then, can we reuse? And this is actually where aviation industry does a really good job. Right? I don't want to be only negative today. So we come again to this picture, right? This aircraft boneyard. We said, okay, maybe it doesn't make you so happy if you're thinking from a circularity point of view. But if we zoom in, we can start to notice some things. There's a lot of parts missing from these planes, right? We see a lot of engines that are gone. Here and there we see some doors or nose cones that are gone. Right? And that is because parts of these planes are reused. And why is that? Well, for various reasons. One is that planes are expensive, but so are the parts of planes, right? So if you think, for example, this is an Airbus A350, the list price is about 100 million. That's difficult to find exact numbers, but it's somewhere in that order of magnitude. The engines on this plane are 35 million each, right? So 70 million for the engines. So about 20% of the price of the plane, or the value of the plane, is in the engines. And that means if you retire the plane, well, maybe the engines are still good and someone else might like to use them, right? And the same for many other parts. You know, if you look at landing gear, it's going to depend on the type of plane, how big and complex is that, but you're talking several million for a landing gear leg and the wheels. The auxiliary power unit, which is used to generate electricity when the engines are not running, 500,000. The blisk, which is just one part of the engine, right? This sits at the front. This is an integrated part where all these blades are integrated with this disc. Very complex to manufacture because it needs very precise tolerances and very difficult materials to work with. 1 to 2 million. And there are many other parts of the plane that all still have a lot of value, right? And so even if the plane itself reaches the end of its life for whatever reason, which can also be for economical reasons or strategic fleet planning reasons, not necessarily fatigue or really structural reasons, there may be lots of parts on the plane that are still good and are still usable for other parts. What we also see is that plane families or series can have a long lifetime, right? Planes might be in production for 20, 30 years, which means that you may be retiring the first plane of the production series while the last plane is still being delivered. And that means that there may be a demand for spare parts, and instead of making new parts to use as spare parts, you can take those off older aircraft that you're decommissioning. And there are, in fact, a number of companies working on this. One example, this is AELS. They're in the Netherlands themselves. Maybe also interesting to invite for a talk at some point. They're located at Twente Airport, Aircraft End-of-Life Solutions. And if you go to their website, you can see they have two main offerings. You can buy their parts, or you can sell your aircraft, right? Because this is the business model. ALS buys old aircraft. They take out all the parts that are usable, and then they sell those parts to people wanting spare parts. Right? And the fact that this is a successful commercial company shows that this is a business model that works. It's an economic model that works. So there are two aspects to why is this possible. One is that we have these high value components that people are wanting to use because there's still aircraft of that type flying around, or aircraft of similar types that use the same components. And the other is that the aviation industry is very regulated and very documented, right? So whenever there's maintenance on an aircraft, there's extensive record keeping. You see one example here, right? They're full all kinds of technical logs, worksheets that are signed off, inspection reports, and those are all kept with the aircraft. So not only do you have high value parts, but you also have all the documentation to be able to trace the lifetime of that part, to see exactly what has happened to it, and to guarantee its condition, right? Which helps set the stage for being able to reuse this part in a new situation, even in a very safety critical situation, right? And so if you look at the ALS website again, you can see there are many parts, right? So I showed you some examples, but you can see pylons, pipes, oxygen bottles, lights, lavatories, landing gears, inlets, doors, ducts, many, many parts that you can buy that all can be given a new life after the decommissioning of the aircraft. Yeah. So in summary, reuse is something the aviation industry is really good at. Maybe even give you an example for other industries. I will give some numbers to how many components are used in a bit, but I think for me the reason why is it possible, well, there is a large market for reuse, right? So there are many people that want these spare parts, and we have a lot of high value assets, right? If it's a part that's worth $1 million, it's worth the effort to carefully dismantle it and take it off a plane and store it carefully. And these assets, these parts are very well documented, so there's a lot of traceability that allows you to guarantee the quality of the part that you're getting, right? Yes, it's of course second-hand, but you know exactly how much life is left. You know that nothing strange has happened to it during its lifetime, or if it has, that it's been repaired properly, right? All of that is available in the documentation. Right? The documentation is also very important. If you lose the documentation, the part itself is also immediately worthless. right? And will even be scrapped to make sure that it's not counterfeited. And so that is why reuse is possible. But not everything can be reused, right? We've talked really about components that can be reused, but the skeleton of the plane, the structure, that's not so easy to reuse, right? You can't just take a wing off one plane and put it on another plane. So then we're left with the lower rung of our pyramid, which is recycling. Right? And then again, we come back to this point. We have here our boneyard, right? We've taken out the valuable components. What do we do now with the rest of the plane? Now, you might say in theory, especially for current generation aircraft, they're made of aluminium. Aluminium is extremely recyclable. I think the quote is, what's it, something of 75% of all the aluminium ever extracted from the earth is still in use because it's so recyclable. So in principle, recycling a plane is entirely possible, right? If it's an aluminium plane, you know, chop it up, melt it down, reuse the aluminium. There are some challenges with that, which I'll come to, right? But one is especially, what do you want to do with the aluminium? Do you want to use it for beer cans, or do you want to use it for a plane again? And especially if you want to use it for a plane, we start to run into some challenges. But before going into detail on that, just to give you some feeling for the study, there was a study already 20 years ago now, a European project called Pamela, I think run by Airbus with various partners. They took an old Airbus aircraft, an A300, for those of you who know your aircraft, and they spent 2 years really step by step recycling it, finding what can we do with this plane. You can see there were a couple of steps to it. So they cleaned and decontaminated the plane. Then they thought about, okay, what can we extract? How can we use it? They disassembled all kinds of parts, which were via repair shops, were then reused as spare parts in aircraft. And then they had some material left where they tried to find as best recycling solutions as possible. And so what they found, and this is already 20 years ago, 85% of the weight of the aircraft could be recycled, reused, or recovered in some manner. Right? So of the 106 tons of starting aircraft, 61 tons could be recycled, 13.5 tons went to conventional disposal, so probably something like landfill or burning, depending on the material. And the remainder, that's then the components that could be reused, engines, landing gears, pumps, those kind of things. So technically, it's just very possible to recycle an aircraft, right? It's not a technological challenge. So why don't we just do it? Well, there are some other challenges, right? There's classic one, contamination. There's the cost of dismantling. There's production volume, and there's certification. So contamination, well, the issue there is that we like to make a plane not just out of one material, but out of many, right? Because different materials have different advantages and disadvantages. And so what you try to find is different aspects of the plane, different parts of the plane. You need different properties. So you find the material that is most suited for that part of the plane. Here you see one example of an Airbus A380. The main point is you see the different colors. The different colors are different materials, right? So you see yellow here is glass fiber reinforced polymer. Blue is carbon fiber reinforced polymer. Green is glare, which is a combination of aluminium and glass fiber. And in white, there's the aluminium. Right? So if you just put this plane through a very big shredder and have everything on a big pile, that's going to be very tricky to recycle, right? Because you're mixing up all these materials. You can melt down the aluminium, but you can't melt down the carbon fiber. That will just burn. So if you want to recycle this, you need to separate out these materials, right? So you can treat each material individually properly, that you're not contaminating. There's also, of course, usually paint on top of all these materials. So you may need to clean that off if you want to recycle the materials properly. I'll also point out what I just said, aluminium is very recyclable, but you see this plane, all these blue parts are carbon fiber reinforced plastic. That's becoming more and more important as a material in aircraft. The latest aircrafts are 50% made of carbon fiber reinforced polymers. And those are much harder to recycle, right? Those you can't just melt down. There are some recycling techniques, but they all have their disadvantages. And it's very hard to really recover pure virgin material properties, unlike with metals, right? If you do your recycling carefully with metals and prevent contamination, you can get basically the same material back again. But the story gets even trickier because, okay, here we see this nice parts in white, right? That's all aluminium. But aluminium is not aluminium. What do I mean by that? There are many alloys of aluminium. But here you see another example. This is an older plane that is mostly aluminium. But you see all these different mysterious codes. The key thing for today is that each of these numbers represents a different alloy, which means a different composition of aluminium and other elements that together make up the material. And if you have a different alloy, you get different properties, right? And again, so for that reason, some parts are made of one alloy, some parts are made of another alloy, depending on which property we want. But if we recycle this plane and just melt it down all in one go, then whatever comes out is some mix of these alloys, right? It's none of these alloys, so it doesn't have the properties of any of them, but it's some kind of weird in-between mix that probably we don't have a use for. So if you want to recycle this, at least to a high-value product, then you need to separate out these different alloys, which means you need to know which alloy is where, and you need to disassemble them, right? Carefully to be able to separate it out. Which is tricky because for economic reasons, if you want to do things cheaply, this is how you would like to disassemble your aircraft, right? This kind of big overhead crane, big bandsaw in between, zip, chop it up, or with one of these grabbers, just tear the plane apart, throw it on a big pile, cart it off to be recycled, right? That's what you would like to do. But if you look at this fuselage barrel, probably at the top, the aluminium alloy used is different than at the bottom, right? So if you want to separate it out, if you want to recycle to the same alloy again, to have high value properties, you need to disassemble it more carefully, right? There has been research into that, for example, in the Sustain Air project, right, where people looked, okay, can we use some techniques to find out, what is the structure like? Because you see from the outside, we have the skin, but inside we have all these reinforcing structures. So you need to take that into account when you're cutting up your structure recycling. Maybe we want to cut along a joint or around the joint, or, do we need to separate out the stringer or this rib or not? So you need to visualize that. You also see these rivets. Typically, rivets are not made from the same material as the skin. So again, you have now a foreign material that you need to take out if you want to recycle, right? But in this way, you could, with a robotized solution, make a very neat cut along some of these joints. And in principle, separate out the panels. But it's going to be more effort and more work than if you just take your big crane and go. So again, there's a challenge. And you might say, well, if we know we're joining all these different materials together, can we not make joints that are easier to dismantle, right? That you can just very easily screw apart, or that is more modular? Can we avoid things like welding, where we really join parts together in a way that's very difficult to separate? In theory, yes, but that would add more mass to the aircraft, right? We saw before why we don't want to add more mass, right? So maybe there are things you can do in the design to improve recycling, and of course we should look into that. But as soon as the impact of that is that we add more mass to the aircraft, it's maybe not worthwhile to do. Another challenge is the cost and the low volume. So it's a bit hard to find numbers on this, but some things I've been told by people at ALS is that the cost of scrapping a plane is roughly equal to the value of that scrap, at least with current technologies and the current ways of sorting. So that means that the only real reason to do it is because you need that space on your lot, right? So if you are space constrained, you only have a small area like in the Netherlands, okay, then it's worthwhile to at least get rid of the plane, even if it's break even. But yeah, if you have a large tract of desert and you can just say, well, just shove the plane in the corner and I forget about it, then why bother to dismantle it, right? Why bother to recycle it? There's also an issue with low volume, right? So we have these very niche aluminium alloys that are used only for specific applications. And if you look, the annual production of aluminium is about 70,000 million tons per year. I did a rough estimation. If we assume something like 500 to 700 aircraft being retired per year, which I think is a reasonable number at the moment, but other people may have better numbers on that. I see we have Ligeia from ATOS here, for example. She may know. Feel free to correct me. But they have a very rough estimate. We are at 0.035 megatons per year, right? So this is a tiny fraction of the total aluminium market. So if you want to buy aluminium, are you going to go to a lot of effort to try and recycle that small amount of aluminium, or you say, forget about it, I just buy new because there's a massive market and this is too small to be worth worrying about to really invest in or see what we can do with that. Right? Another issue is that dismantling, especially if you do the chopping up, in a let's say time efficient way, in a therefore also cost efficient way. If you're a specialized company, you can shred a plane in a day. Okay, great. But how many planes are you shredding every day, right? If you only have, 2-3 planes a month that you're recycling, what is your shredder doing the rest of the month if it can shred on those planes in 1 or 2 days? Right, so you gain a lot of downtime and it becomes an economic issue. It's not then interesting to invest in such shredding equipment if you can't be using it all the time. A last challenge to recycling is certification. It sometimes comes up. So people often as a shortcut say, okay, if we want to use materials on aircraft, they need to be certified. And then a challenge for recycling is, okay, if I recycle material, I need to certify the material. It's actually a little bit of a misconception because you cannot certify a material, at least not from an aviation point of view. What we certify in aviation are products, that is, the entire aircraft. So what happens? The designer makes a certain design and says, okay, this design needs to have certain properties, certain strength, certain corrosion resistance, and so on. To achieve those properties, this specific material has to be used for this part, right? So they might say, for example, aluminium 2024 T3 needs to be used for this panel. Right? And then they prove with calculations and tests that if you use that material, then the part has the right properties. And this specification is very tight, right? So there's a document kept by, in this case, Aluminium Alloy Association of America, I think it is, or Aluminium Association of America, right? But there's bodies that keep a standard that says, okay, Aluminium Alloy 2024 T3 means exactly this, right? It means this percentage plus or minus this amount of aluminium, this percentage plus or minus this amount of copper, and so on. So if I go to any aluminium supplier in the world and I say, I want aluminium 2024 T3, then I can be pretty sure of what I'm getting, assuming they don't cheat, right? But if I check that, but I can go to any aluminium supplier I want. I say, I want aluminium 2024 T3. I know what I'm getting and I know what properties it will have, right? And so I certify my plane saying, okay, this part is made from 2024 T3, therefore it's good enough, right? And then during the actual manufacturing, the manufacturer has the responsibility to ensure that the material they use matches the specification provided by the designer. Okay? And that's then how it works. So the designer doesn't have to say, okay, you have to buy from the supplier. They just say, you have to make sure you use 2024 T3. It's up to the manufacturer how they ensure that. Right? So how does that work then for recycling? Well, it means that basically there's 2 routes for recycling. If you want to read this in more detail, you can look up this public deliverable from the Sustain Air project. So if you want to recycle material and get it on the plane again, get onto certified aircraft, there's 2 routes. One is that you can recycle material to meet existing specifications, right? So for aluminium alloys, for example, we have these AA codes. So if you can take a old plane, scrap it, recycle it, and then you get a block of aluminium out, and you can guarantee that that aluminium you get out of that recycling process meets the specifications of aluminium 2024 T3, or whichever other one it is, then you can just sell it as that, right? And then it doesn't matter for this process, is this virgin material that was bauxite 2 months ago, or is it for recycled from a plane? As long as it meets the specification, you could use it. Right? The other option, and that's what you may need to move for if we want to recycle composite materials, is you could create a new specification. Say, well, I can't get exactly this material that already exists, but I can make a new material from a recycled material, and I can specify that material, right? I can write all the properties that are of interest and say, well, it will have this composition, it will have these properties, and I can guarantee that I get that every time within a certain bandwidth. Then you could specify your new material, and then your designer could say, in this part, this panel should be made from recycled material XYZ, and that's specified, and again, that would be allowed from a certification point of view. Right? The key questions there, of course, though, are, can you guarantee consistency? So can you guarantee that your recycled material always conforms to the specification that you've written up? And can you guarantee production volume? right? Because if I'm going to build 1,000 planes and I'm planning my production line, and I go to you and say, hey, I want to buy some of your recycled material to make my planes out of, and you say, oh yeah, that's fine, I can do that, but this month I'm getting 10 planes in, and next month I'm only getting 1, and then I don't know where my next plane is coming from, and I can't guarantee for the next 10 years, how much supply I will have. It's not a very attractive business proposition, right? So these are some of the challenges to recycling. So to summarize that, material recycling is technically feasible, especially for metal aircraft, right? We know how to do it. It's entirely possible, but there are a lot of economical challenges to actually doing that in practice, right? So maybe the solution there is technical. We say, well, we need better recycling techniques that bring down the cost of recycling, then it becomes economically feasible. You could also look to regulatory solutions, where you have like these product liability mandates, or where you say, okay, Airbus, if you make a plane, it's your responsibility, it's recycled properly, even if it's 50 years from now. Could be a solution, right? You just impose that people have to take these costs. But the tricky thing with aircraft is they're very easy to fly from one part of the world to another, right? And how do you ensure that people don't just fly the plane to Africa or South America or the US and then sell it there and say, oh, well, I sold it to this person in the US and it's their responsibility now. I can't control it anymore. That would be hard to enforce. All right, summing everything up, what are the main conclusions to take home with you? Achieving circularity in aviation is very challenging. I've shown you what some of those challenges are. Contrary to many other sectors, we have an overwhelming impact of the use phase, right, of the fuel that we burn by flying aircraft around. And because of that, some of the kind of rules of thumb for achieving circularity, like make the lifetime as long as possible, maybe do not apply if you do really a systemic analysis of your aviation sector. Recycling is technically possible, but economically challenging. But to end on a positive note, in terms of reuse, the aviation sector is very advanced, and maybe there are things there that other sectors could draw inspiration from to improve circularity in other sectors. And with that, thank you for your attention and open for any questions.
Thank you, John Allen. Very nice illustration of how important it is to really look into the specifics of the context when it comes to circular strategies. Although I also see that there are, for instance, already similarities with things like washing machines and refrigerators, where you also do not want to design for as long a life as possible because of the use phase advantages that you get when you buy newer equipment. But we only have a few minutes left for questions because we have a hard end time at 11. So, Zea, can I give you the word for the first question?
I feel sorry for John Allen. Hi, Ruth. Thanks for the question. Yeah, so I just want to comment briefly and leave space to Gloria for her question, because, I mean, indeed, nothing of what you, John Allen, shared is, conceptually wrong, but I really miss the connection to circular economy for a lot of the information, the facts you shared. And I perhaps want to point that, especially like your emphasis on the long life aspect. That's not per se like wrong, or it will not be wrong to go to a limited life as a strategy. So that was perhaps the remark. Is you gave a very good view of how the sector is now, but I really missed that link, and I think we should discuss this offline more, because I'm really curious.
Yeah, happy to. Thanks for the comments. Yeah, no, indeed.
Yeah. So Gloria, please ask your question now.
Gloria?
Very softly.
Yeah.
Is it better?
So,
hello?
Yes, now we can hear you.
Okay, yeah, sorry, I had a problem with the microphone, too many settings. Okay, thank you for the presentation. It was super, super interesting. I just have a question about, like you talk a lot about the material in the outer, like the shell of the aircraft. But what about the rest, like tires, the seats, and so on? Like, sorry, it's a very maybe specific
yeah.
question, and
No,
I know
not
that
at
is
all.
like, okay, is it? Yeah, I mean just that, and then I don't think I have time for another one, but let's see.
Yeah, fair enough. No, yeah. So to be honest, that's also a bit because of my expertise. So I work more with the structure. But indeed, so of course there are many different materials. As indeed tires in the interior, there's all kinds of materials for insulation, for fire protection. There's carpets, there's the seats and stuffing and so on. So also part of dismantling the plane is indeed finding solutions for that. Yeah, very true.
Okay, so what happened right now to them? Because I guess also there are many chemicals involved, like I guess maybe some PFAS and stuff.
Exactly. Yes, I think a challenge is anything in the cabin needs to pass fire testing. So there's a lot of flame retardants used, which, to my understanding, make recycling often tricky or even proper disposal. So yeah, Ligea might actually know more about this than me. But as far as I know, so for the recycling companies, when they buy the plane, the tires are on there, the interior is still in there, so they will try to find some kind of solution and ideally something they can earn money. But yeah, definitely something to take into account when dismantling a plane.
Okay, but like today, what happened? Like, is it burned? Is it like go to landfill? Is it like exported?
See Ligea nodding. I don't know if you want to comment.
Currently, interiors are mainly landfilled. As John Allen said, like if there's fire retardant, it's pretty easy. It's pretty difficult to incinerate them. So you don't really want to go there, but those are the path right now. And there's tons of research specific on interiors going on now.
Okay. Thank you.
You're welcome.
Okay, and I'm convinced there are more questions, but we don't have any time left. But I guess that people who have a question can just send you an email. So thank you once again for a very nice presentation, and thank you all for your participation. And I hope to see you again in 2 weeks' time. Have a nice day.
You're welcome. Have a nice day. Bye-bye.